So we're going on to chapter 4 here, which is on polynomials. All right. So let's just talk about the basic terminology. All right. So what is a polynomial? So I'll start with the name calling. All right. So a polynomial is built from things called like monomials. What's a monomial? Something like x, right? Or x squared, right? Or you could have 3x to the fourth. These would be examples of monomials because they have just one term. All right? Now, a binomial would be something like x squared plus 3x. See, it's called a binomial because it has two terms, right? And then that brings us to what's called a polynomial. Poly meaning many, something like this. Well, I'll give you a specific example. X to the fourth plus 3x cubed plus x plus 1. This would be an example of a polynomial in x. All right? You could also have a polynomial in another variable. Like this is a polynomial in x. You could also have something like a to the 13th power plus a squared. This would be a polynomial in a. Right? So some of your homework is in terms of x. Some of your homework is in terms of like other letters like v. But the same rules govern no matter what letter we're using, okay? So let me give you a little bit kind of more formal definition, all right? Definition. A sub n, x to the power n, plus a n minus 1, x to the power n minus 1, plus dot dot dot, plus a squared, a sub 2 x squared, plus a1 x, plus a sub 0. This is a polynomial. All right, let me be more specific. Where a0, a1, a2, all the way on out to a sub n, these are all elements of the real numbers. So these are all elements of the real numbers. These are called the coefficients of the polynomial. All right, the coefficients. These are the coefficients. And we make an assumption here. All right? We want to assume that a sub n is not equal to 0. Now, if a sub n is not equal to 0, all right, a sub n, this is called the leading coefficient. All right? Now, it's helpful to just give a name to the polynomial for the sake of discussion. So, since it's a polynomial, let's call it p of x, all right? So let's just call this whole thing p of x, all right? And with respect to that, we define the degree of p of x is equal to what? Well, the degree of the p of x I just wrote is n, all right? The degree is the leading coefficients order, if you will. So that's the basic terminology that we need to use, right? So now that I've told you this terminology, you guys tell me. Let's look up at the top here. The monomial x, what are the coefficients here? Well, there's a coefficient of 1, x to x, and then there's also a coefficient of 0, if you can use your imagination, right? Because like x, x is equal to 1 times x plus 0. So like the coefficient here would be a1 equal to 1 and a sub 0 equal to 0. All right? How about x squared plus 3x? Oh, goodness. That stupid cough sneaks up on me sometimes, guys. Phew. X squared plus 3x. Can you tell me? What are the coefficients here? 1 and 3? Right. Well, almost. Let's see. So we would say that this is like ax squared plus bx plus c. So in the context of like a quadratic polynomial, we like to use a, b, and c for the coefficients. That's just our custom. All right? You guys remember the quadratic formula from high school? Maybe? What's that? The quadratic formula, remember? Like x is equal to minus b plus or minus the square root of b squared minus 4ac. We'll get to that eventually. But my point is that's the a, b, and c. These a, b, and c's. So specific notation for the quadratic case, so n equals to 2 is quote-unquote quadratic polynomial. All right? And so, like when you compare x squared plus 3x with ax squared plus bx plus c, I mean, what is a equal to? 1, right? A equals to 1. What's b equal to? 3. What's c equal to? C is equal to 0, right? So it's as important to recognize that there's a 0 coefficient as it is to recognize that there's the non-zero coefficients, all right? They both play a role. So how about this one? What's the degree of this polynomial here? 13, right? Because 13 is the highest term that appears. All right? And this one here is order 4. It's degree 4. All right? Everyone understand? Everyone on the same page? We got it? So basic, fact, if you have an x to the n plus plus like a2x squared plus a1x plus a0 equal to, say, bn x to the n plus plus b2 x squared plus b1x plus b0. One of the basic facts of algebra, if we have two polynomials like that, we can be sure that their coefficients are equal order by order. So like then we have an equal to bn, and so forth on down the line. We have a2 equal to b2, we have a1 equal to b1, we have a0 equal to b0. So this is called equating coefficients. This is a basic idea that we should keep in mind, all right? Because if we want to judge two polynomials are equal, the question is, do they have matching coefficients? You can judge whether they're equal by that. Now, let me show you an example. So, example 1, suppose we had x cubed minus 3x plus 2 equal to ax cubed plus bx squared plus cx plus d. Can you tell me what a, b, c, and d are? Can you put into practice the result I just wrote above? Well, a is 1, right? A is equal to 1. B is equal to what? B is not equal to negative 3. Notice that it's a trap. Right, so like to be explicit, let me write this over here just because I ran out of room. So this would be x cubed, right, plus 0 times x squared minus 3 times x plus 2. See, that was the trap. B is 0. Now what's c equal to? Yeah, C is equal to, what'd you say, minus 3? D is equal to 2. Very good. Okay, so that's the first order of business, is understanding coefficients. I hope we're there. All right? So the next order of business is how do we add or subtract or multiply a polynomial by like a number. All right? And so I'm going to illustrate that with examples. All right? Suppose we have x cubed plus 3x squared minus 7. And when we want to add to that x to the 5th plus x squared minus x plus 10. All right, we want to add these two polynomials. All right? So what's a good practice for adding them? Well, I think a good practice for adding them is to try to identify the leading term and write that first, right? So like, by the way, the polynomial I wrote in the definition, this is quote-unquote standard form. Standard form is when you write from like highest order to lowest order, all right? That's kind of important, right? Because if we're going to both talk about polynomials and you like put all the orders all kind of jumbled up, it's hard to judge whether or not we're talking about the same polynomial. But if we always like list them from highest to lowest, then we can kind of have a common understanding. So this one, what's the top? I mean, what do you got? You got x to the 5th, right? And then like, what's the next highest thing? Plus x cubed, right? Now, where it gets interesting is when we have overlapping powers, right? So I have a 3x squared here. I have an x squared here. What happens when we add them? We get 4x squared, right? So we have to add apples to apples and oranges to oranges, so to speak, right? So we wouldn't add a cube to a square. We wouldn't add a fifth power to a fourth power. We have to add like powers. That's the only thing we can combine. All right? So there's that. And then, of course, we have, what else? We got minus x, right? That's the next thing. And then, again, we have common constant terms. So these can be combined because they have the same order. They're order 0. So 10 minus 7 is 3. All right? And there you go. So the key for adding or subtracting polynomials is we must add like terms. All right? Identify like terms and add them. And don't make up things that aren't like and make them like don't do that. So, example 3. Here we go. 3x squared plus 7x minus 10 plus 2 times x squared plus x, like that. All right. Now something like this, I think we should make an in-between step before we try to do it all, since we're starting here. All right, so how do you do 2 times a polynomial? How does that work? So I'm just going to copy this down again. This is 3x squared plus 7x minus 10. So how do I multiply 2 through? I go 2x squared plus 2x. All right. Now we can add like terms, right? So what do we got? 2 plus 3, 5x squared, right? That's from this one and that one. Are there any other x squared terms? Nope, that's it. How about x? And we got this 7x, we got this 2x, so that gives us 9x. Very good. And then what are we left with? That minus 10. And so there you have it. All All right, so again, the key is combine like terms. And I guess I should just tell you definition. Definition, if we have a constant times a polynomial, the way that works is you do a constant times an plus the constant, plus dot, 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 constant times a2 x squared plus a constant times a1x plus a constant times a sub 0. What I'm saying is when you multiply the polynomial by a constant, you multiply every single term by that constant. This is how it works. Let me give you an example. Just to drive this point home, if I have 3 times 13x cubed plus 2x squared minus x, all right, then that's equal to 3 times 13 x cubed plus 3 times 2 x squared minus 3 times x. In other words, 39 x cubed plus 6x squared minus 3x. All right? Now, I think the things I've told you thus far don't really give you guys difficulty. Most people are not going to struggle with this part of it, right? You're kind of bored, probably, right? I hope you're a little bit bored with what I'm showing you at the moment. What we're about to do, though, is where you guys start to have more of an uphill climb. There's something a little bit trickier to learn, all right? And that's in the problem of multiplication. How do we multiply polynomials? So, ultimately, these polynomials, they're a way to describe a formula, right? I mean, if you put some of these formulas into Old English, they're kind of horrible, right? Like, for example, this one. You take the quantity and multiply it by itself 3 times, then take 3 times the quantity, and then add a sum of 2. I mean, that's what you'd have to write as an English sentence to express the idea that you take x and do this thing to it. So it's an incredible efficiency of notation to be able to just write x cubed minus 3x plus 2. Right? This is why we can do algebra, and why back, 500 years, 600 years ago, only mathematicians could do algebra, because they didn't have this notation yet. They had to write things out in like sentences. It's horrible, right? But thanks to Arab, I think it was, algebra, that's an Arab word, right? That's where we started having this symbolic way of thinking, and then ultimately, flourished in Europe in the 15, 16, 1700s and so forth. Here we are today. But anyway, multiplication. So the basic thing is the distributive property. Do you guys know what the distributive property is? Here it is. If I have A times B plus C, it is AB plus AC. That's the distributive property. And that essentially is going to guide our multiplication of polynomials. All right? Let me give you an example. Multiply x times x cubed plus 3x squared. All right? So the way this works is we use the distributive property. We have x times x cubed plus 3 times x squared. I moved the x past the 3, okay? Now, I should mention, there's another key property, right? Which is the laws of exponents, namely that if we have x to the m times x to the n, what do we get? How does that work? We get x to the m plus n, right? We add exponents. So that's also a key property here in this story of multiplication. So now let me, so x is really what? Really x is x to the 1, right? Remember, x equals x to the 1 power. All right? So what do we have? 1 plus 3 is 4, right? And we have 3x cubed. So there you go. Shall we do another? Let's do another. What's that? Just add the top, right? Yeah, let's do more. Let's do more. What if we were going to multiply x squared times x to the 10th minus 3? So again, we use the distributive property. We have x squared times x to the 10th minus 3 times x squared. So the second term is kind of easy here. There's really nothing to do, right? We just got that minus 3x squared. Great. But how about x squared times x to the 10th? You said you just add the top, right? 12, right? So we got ourselves x to the 12 minus 3x squared. There you go. All right. Let's do another. What if we had x cubed times 3x plus 2 minus x squared? See, now I've got 3 things. But guess what? The distributive property for 3 things, it works just the same. All right, so like if I had a times b plus c plus d, it is ab plus ac plus ad. Same song and dance. All right, so that means I go 3 times x cubed times x plus 2 times x cubed minus x cubed times x squared. Excuse me, I must ingest a candy. So did you guys enjoy your day off? I slept. I slept so much. I didn't realize how tired I was. And I also got a bunch of homework done, which was exciting. I enjoy doing homework. I know. Strange, right? Although I guess it's hard for you guys to understand me. I mean, like, I want to do nothing but math my entire adult life. You want nothing but for this to be your last experience with math, right? You want to leave it behind you. Am I right? I understand that. I do. I mean, I don't understand it, but I understand it. It's a strange thing. My daughter is taking an English class right now, freshman comp, from like she's in the dual enrollment program at like University of Alabama. We homeschool. And like she has, her professor said something along the lines of like, she didn't understand the math. And I don't know how Hannah is writing about math in her freshman comp, whatever she's doing. It seems unwise to me. Like, why is she doing that? But it's just funny to me that like an English professor is comfortable saying they don't understand math. How would you feel about a math professor who says, yeah, I don't really understand how to write English? Like, it would be frowned upon, pretty sure. And yet, in our society, we've accepted like mathematical apathy. I don't know. Maybe it's part of what's wrong with society. You need English more than maths? See, my sister and my little sister got in arguments. Well, not cheating an argument, but with a math guy. Like, well, what are you thinking? And of course, you want to hear. I mean, what do you think in? You think in words? her friend is like, no, I think in numbers, because he knew where the argument was going. But anyway, I digress. Okay, so add the top, but we have to understand what the top is, right? So x is x to the 1. So we've got 3 times x to the 4th plus 2x cubed minus x to the 5th. Now, if I want to write the answer in standard form, is it in standard form right now? It is not, right? Because I want to write the 5th order term first. So it's a simple thing. You can put the terms in any order you want, really. It's just for the sake of custom, we write it in descending order, because then if you write your polynomial in standard form, then you can look at it and you guys can immediately tell me, oh, that's a 5th order polynomial. The leading coefficient is what? What's the leading coefficient? What's that? No, the leading degree is 5, but what's the leading coefficient? -1, right. Yeah, because, minus x to the 5th is a notation that we use in place of -1 times x to the 5th, right? Because writing -1 times x to the 5th is kind of a drag. It's a lot easier to just write minus x to the 5th, but those mean the same thing. All right, so the multiplications we've done so far, they've been pretty easy, right? Because we're just multiplying a monomial times a binomial, or a monomial times a trinomial, so we just distribute, right? What happens, though, and this is where we have to start thinking a little bit harder. How do we multiply, actually, did I move my camera? This occurs to me, I may have been off screen here. Oh no, my bad. Sorry to those of you who are not here. Oh, that's unfortunate. Well, anyway, sorry. What if we want to multiply something like x plus 3 times x squared plus 2? See, how does this work? Well, we can use the distributive property again. So this is x plus 3 times x squared plus x plus 3 times 2. All right? But we're not done, right? Because we can use the distributive property again to multiply those terms. So what do we get now? We get x times x squared plus 3 times x squared plus x times 2 plus 3 times 2. Now what's x times x squared? That is x cubed, right? So we got, goodness. We've got x cubed plus 3x squared plus 2x plus 6. And there you go. Now, I'm trying to take you back to base principles to show you it's really the distributive property done twice, right? But we can also just sort of memorize a pattern when we want to multiply a binomial times a binomial, right? So like, what's the pattern? You have a plus b times c plus d. How do you do it? Well, we've got a plus b times c plus a plus b times d, right? And so what's that work out to? That works out to AC plus BC plus AD plus BD. Let me see here if I can find a better way to communicate this to you guys. Well, let me just go ahead and I want to do some color coding here. So if you don't mind, I'm going to just write it right there instead. So I've got A times C plus BC plus I'm going to write BD next. And oh, no, I don't want to write BD next. I'm going to write, sorry guys, well, yes I do, BD. BD, and then finally plus. Sorry guys, I'm having I wanted to write 80 there. I'm just having a crisis of choice. All right, so look, here's the pattern. I think it's helpful to look at it graphically. So to multiply A plus B times C plus D, what we're doing is we're multiplying this times that, right, to give us this right here. So like the first times the first, we write that for like that. Then you're looking for the middle terms, like B times C. That's this one, right? And A times D, like this here, right? And then finally, you also have to multiply what? Yeah, the last times the last. Yeah, I believe this is called the FOIL method. First, outer, inner, last, right? First, outer, inner, last. Now I don't. This is not something I teach. I'm reminding you. You were told that before. If you understand that, great. I do not think this way. I think in terms of distributive property. All right. But listen here. There's something more to think about, which is if we multiply two things times two things, there are in principle 4 terms. All right. We're going to see that if we take 2 things times 3 things, there are 6 terms. If you take m things times n things, you get mn terms. So you can always like count to make sure you're not missing something, all right? So like if I multiply 2 polynomials, if I multiply 2 binomials, like 2 things and 2 things, and I only write down 3 things, that means I'm missing something, right? So anyway, enough blathering. Let's look at some examples here. I think really I probably should have just spent all our time on examples and not tried this general blah, blah, blah. But here goes. All right, so I'm going to try to follow my guide. So I do 3x times x, right? Plus 3x times minus 7 plus 2 times x plus 2 times minus 7. Let me just write the color coding again down here. So I'm like doing this times this to give me that, right? I'm doing this times that to give me that, right? I'm doing this times this to give me this. And then finally, last but not least, I'm doing 2 times minus 7 to give me the last term. Now, I suppose we should simplify our answer, right? We can collect terms. What do we got? We've got 3x squared minus 21x plus 2x minus 14. Oh, I'm not done, right? Because we can combine like terms. What's minus 21 plus 2? Minus 19, right? So we got 3x squared minus 19x minus 14. So, you know, I just got done saying when you multiply 2 things times 2 things, you get 4 things, right? You're like, but that's not 4 things, you got 3 things, right? Why did we get 3 things? Yeah, because 2 of the 4 things combine, right? So this is going to happen when you multiply polynomials that have like the same order. You're going to get overlapping terms. let me show you this doesn't happen if we multiply polynomials with like not matching orders. So something like, 1 plus x times x squared plus x cubed. All right. If we multiply something like that, we're going to get 1 times x squared plus 1 times x cubed plus x times x squared plus x times x cubed. By the way, my internal logic for how I multiply, here's how I think about it. I think about the 1 distributing through this x squared and x cubed. So the 1, this 1, maybe you'll find this pattern more appealing. This 1 times that gives me these two terms, right? This x times that gives me these two terms. That's actually how I organize my thinking. I don't FOIL. I've never FOILed. It doesn't really make sense to me. But people teach it, so there must be a reason for those people. I distribute. Anyway, how about those terms? Well, check it out. The last, we got what? We got x squared. Come on, marker. Every so often, one of these caps just will not come off. X squared plus x cubed plus x, oh man, curses. This is not the example. They still combined. Man, this is not the example I wanted. I was wanting it to stay 4 things, but look, we can combine the x cubed. My bad. It's because the 1 times x cubed is order 3, but x times x squared is also order 3, so of course they combine. You're like, it doesn't, it's okay, just move on, right? All right, fine, yes. Oh man, which one should I write first? Which is the biggest guy in the block there? Yeah, 4. X to the 4th plus 2x cubed plus x squared. There we go. All right. Let us do another. So here, you guys try to work this out. What if I had x plus 3 times x cubed plus 2x squared minus 8? How's this going to work? So what we're going to do is we're going to basically use the distributive property again. So we do x times x cubed plus 2x squared minus 8 plus 3 times x cubed plus 2x squared minus 8. Remember what I said? If we take 2 things times 3 things, we're going to get 6 things. Do you see the 6 things? Now we gotta distribute through. So we've got x times x cubed plus 2 times x squared minus 8 times x plus 3 times x cubed plus 3 times 2 times x squared minus 3 times 8, which is 24, okay? Ooh. Sorry if I'm writing too small. I'll try to write bigger. So what do we got? We've got x times x cubed, which is what? X to the 4th, right? And x times x squared is what? 2x cubed, right? Minus 8x plus 3x cubed plus 6x squared minus 24. Now, are there any like terms we can combine? Yeah, the cubes go together, right? And also, nope, that's it, right? All right, so let's get to it here. We've got x to the power 4. 2 plus 3 is 5, right? So plus 5x cubed plus 6x squared, that's the next down the line, minus 8x minus 24. There you go. I'll do one last and horrible example. I will do three things times 3 things. All right? Sound good? No? So if we had x squared plus x plus 10 times x to the 4th minus 3x plus 8, what would we get? So we have x squared times x to the 4th minus 3x plus 8 plus x times x to the 4th minus 3x plus 8 plus 10 times x to the 4th minus 3x plus 8. So it's again this distributive property, all right? I'll do color coding to try to emphasize what I just wrote. So I'm saying this guy times that gave you all these terms. This guy times that gave you these terms. And finally, this guy times that gave you these terms. We have a trinomial times a trinomial. That's 3 times 3, 9 total terms, right? Before we collect like terms, it will collapse down, won't it? So let's see here. We've got x squared times x to the 4th minus 3x squared times x plus 8x squared plus x times x to the 4th minus 3x times x plus 8x plus 10x to the 4th minus 30x plus 80. So again, it's just the distributive property applied over and over again, paired with the laws of exponents. X to the m times x to the n is x to the m plus n. We add the top, right? So what do you got? We got x to the power 6 minus 3x cubed plus 8x squared plus x to the power 5 minus 3x squared plus 8x plus 10x to the 4th minus 30x plus 80. All right. So which is the biggest? Well, x to the 6th is the biggest, right? So it's already out front. That's great. What's next? 5, right? Is there more than one of those, or is that it? That's it, right? So there's just plus x to the 5th. What's next? The 4th power, right? Are there more than 2 4th power? Where's the 4th? Just this one, right? So plus 10x to the 4th. All right. Now I'm going to look for cubes. We got any cubes? I want here. Any others? No? Oh. So minus 3x cubed. What's next? Yeah, to the square second power, right? So squares like this guy and that guy, right? There's 2 of them. What's 8 minus 3? So we got plus 5x squared. Then what's left? Oh, we got the 8x, but we also got the minus 30x. We can combine those, right? Combine like terms. So what's that give us? Minus 22x, right? And then finally, the last but not least, 80. So this is how we multiply polynomials. You're like, is that a question on the next test? Well, ask yourself the question, do I want to grade that? I do not want to grade that. And I can test whether or not you can multiply easily with a problem like this, right? Because if you can do this problem correctly, you can do this problem correctly. It's just a matter of sustained effort, right? And actually, if you can do this, I could put 6 terms here. I could put 10 terms there. You could still multiply it out. You'd have 60 possible terms, right? This goes on. I'm not going to ask you to do those, but I hope that you see the principle that would lead you to allow you to do that, all right? All right, so now that's pretty much all I have to say about multiplication. So what comes next? What comes after multiplication of polynomials? What's that? Division. Kind of, sort of, yeah. That's not, well, that's a good question. Do we ever actually get to division of polynomials in this course? I can't remember. See, my mind is cloudy because I taught this course and pre-calculus. I know we do it in pre-calculus. I'm not sure we do it in here. But we use the word factoring. Factoring. And, I mean, factoring is related to division, right? I mean, let me show you what I mean by that. Just think about numbers, right? So if I tell you guys, 105, find the prime factorization of 105. What is 105 equal to? It's 3 times 35, right? What's 35? 5, yeah, 5 times 7. So it gives 3 times 5 times 7. So that's the prime factorization of 105. So finding a prime factorization of a number, that's kind of like what polynomial factoring is. Of course, they're related to in terms of like the division comment I was going to say. So in this sense, like if I have 105 divided by 3, well, then it's easy to figure that out if you know the prime factorization, right? Because you could just cancel the 3's and you get 35, right? So like there is this interplay between a factorization and division, but we're going to be focused pretty much entirely on the factorization issue. All right, so let me give you a definition. 5 times what?
5 times 21.
Oh, 5 times 21. Ah, yes, very good. That's another way we could look at it. Very, very true. Thank you. Right? Or what? There's another one, isn't there? I mean, there's the really stupid one. Yeah, yeah, you got me. Or if you really want to be an annoying math person, you could do minus 5 times minus 21. What's that? 7. Divide by 7. Yeah, there's all kinds of things we can do. All right, I think I'm getting off track here. Oh, man. Definition. If polynomial p of x is equal to, let's say, f of x times g of x, where f of x and g of x are polynomials, then this is a factorization of p of x. Let me put it into words. To factor a polynomial is to write the polynomial as a product of other ones. in some sense, factoring is like unmultiplying. You could say that. So example 12, let's try this. What if I had x cubed plus 3x squared plus 7x? Can we factor something out of this? Well, let me show you how. So there's a common x, so I could do x times x squared plus 3 plus x times 3x plus x times 7. Right? So I'm identifying that I can factor an x out of every single term. Right? Then by the distributive property, in reverse, if you will, we can factor x out. This is x times x squared plus 3x plus 7. That, my friends, is a factoring of the polynomial. So how do you judge whether or not you've factored a polynomial correctly? What would you do? If you want to figure if you've unmultiplied something correctly, what do? You multiply it. So if you multiply that back through and you get back where you started, that means we factored correctly. We can always check our answers with factoring with multiplying. And we should get in the habit of doing that. All right? Let's look at another pretty kind of easy example here. X to the fourth plus 20x squared. What can we factor out of this? Well, notice we can peel off an x squared from both terms, right? So like that's x squared times x squared plus x squared times 20. See, I've got a common factor of each term. See that x squared sitting there? Like here and here. So I can factor that out by the distributive property. I've got x squared times x squared plus 20. So there you go. That is a factorization of that polynomial. Does that make sense? And we can judge this, whether or not I'm right or wrong, by just multiplying out it. Just multiply it back out. See where you get back to. Right? If we multiply x times x squared, we get x to the fourth. X squared times 20, we get the 20x squared. We get back where we started. All right. So you guys don't usually have trouble with this kind of factoring. This kind of factoring, you know, we can do this part. If you're just like peeling off an x to some power, that's kind of easy to think about. What is trickier, right? What is trickier is the kind of factoring we're about to embark into here. So here's another one. So this is I would say this is our first real kind of non-trivial factoring problem. X squared plus 3x plus 2. This can be factored. So here's the idea. If you look at it, we could put an x here, and we can put an x here, like that. If we do that, we're going to do what? When we multiply it back out, we get the x squared, right? So we've got the x squared. How can we get a 2? How can we get a 2? Well, 2 is 2 times 1, right? It's also equal to minus 2 times minus 1. So we need to fill in the blank like here and here, right? Let me do something that doesn't work. So if I tried, say, minus 2, and I tried minus 1, like this fails, since what? X minus 2 times x minus 1 is x times x minus 1 minus 2 times x minus 1, which is x squared minus x minus 2x plus 2, which is x squared minus 3x plus 2. By the way, you see you got to get faster at polynomial multiplication. If you're going to be successful at factoring, you must get faster at multiplication. Otherwise, the time scale at which you can check your work is prohibitive. So you need to work on polynomial multiplication. Like, you got to be good at it. But anyway, my point to you, this is not that, right? So what should we do? Instead of using minus 2 and minus 1, what should we do? Just change it to positive, and we're good to go, right? Because, well, let me write it down here instead of that. Let me not tear down this mathematical statue. Let's see here, 3x plus 2. So x plus 2, we need to understand the history of our mistakes there, right? So here, x plus 1. Now that works, right? You can multiply it out. We got it, right? This is factoring. Let's see here. How about x squared plus 16x plus 15? So I'm going to start us out. Here's kind of our template. So how can you get 15? What are different ways to get 15? Well, 15 it's 3 times 5, right? It's minus 3 times minus 5. It's it's 15 times 1. It's also minus 15 times minus 1. I mean, there's four flavor choices. You could put 3 and 5. You could put, minus 3 and minus 5. You could put 15 and 1. You could put minus 15 and minus 1, right? Which one should we choose? Now, 15 and 1, right? 15. Exactly, because we think about the cross terms, right? So think about the cross terms. We think about 15 times x and x times 1. That gives me 15x plus x, which gives me 16x. That's what I had, right? So this is the quick check. You have to think about the cross terms, and do they match the middle term? All right? Example 6. Let's see here. X squared minus 11x plus, let me think through this here. $30. All right, so x, I heard a -5 and -6, right? So very good. Now, how did they do that so fast? What was your thought process on that? Right. Right. They have to multiply together to give plus 30, and they have to add together to give the middle coefficient, right? Right. Now, everything we're doing is based on the assumption that the leading coefficient is x squared. This story changes a little bit if we've got like a number in front of the x squared. All right. So we'll talk more about that in a future lecture. But I mean, this is a pretty good start. Now, one other thing I should I'll